Solving a system of linear equations by substitution. So one way to find solutions that's a little more efficient than graphing is to use an algebraic approach. And let's take a look at that through this example. We'll solve this system. 4x and 5y is 26, and 3x is equal to y minus 9. Now, the way that I'll teach you in this section, and there are a few different algebraic approaches, but the way I'll teach you in this section is something called substitution. And in substitution, what you do is, first, choose a variable in one of the equations to isolate. It doesn't matter which equation, and it doesn't matter which variable. However, it is easier to choose some variables in some equations. For instance, in this system, it would be easiest to choose this y to isolate because it's 1y. And it's going to be very easy to solve that equation or isolate that equation for that single variable. If you go and try to isolate any of the other variables, so this x or this y or this x, it will be much more difficult to isolate. And isolate means get it by itself on one side of the equation. So again, isolate means to get it all by itself. So I choose that variable to isolate, and then my next step is to actually isolate that variable. And in doing so, also rewrite the system. So just scroll down here, give myself a little bit more room. When I take the first equation, I don't do anything with it because I'm not isolating any of its variables. But when I isolate for y and make y equal to, I notice I add 9 to both sides, I get y equals 3x plus 9. So there is my new system. Now I substitute that value, that isolated variable, into the other equation. And what that looks like in this case is this 3x plus 9 is going to get substituted in for where I saw a y in the other equation. So the other equation was 4x plus 5, but now instead of y, I substitute in 3x plus 9, just for that y. And then that's not a plus sign, that was supposed to be an equals 26, so I carry that down and let it equal 26. So I substitute the variable into the other equation. Now I can solve for one variable because I have a new equation that only has one variable in it. So I do a little bit of algebra. In this case, there'll be some distributive law. And 19x is equal to, I have to subtract 45 from both sides, which gives me negative 19. Dividing both sides by 19 gives me 1. I solve for one of the variables. Then, as my last step, I need to solve for the other variable. And the way that you solve for the other variable is to substitute it back into either of your original equations. So in this case, I can substitute the x is negative 1 back into 4x plus 5y equals 26, or I can substitute it into the original equation that I had for the other equation, which was 3x plus, is equal to y plus 9. Y minus 9. I can substitute x equals 1 into either of these equations and solve for y. And I'll show you that it works in either equation. So that's negative 4 and 5y is equal to 26. Add 4 to both sides to give me 30. Divide both sides by 5 to give me 6. In this case, I substitute that negative 1. I get negative 3. I add 9 to both sides, and I will get y is also equal to 6. And I write my final answer as x is minus 1 and y is 6. Let's take a look at another example. And so one big advantage with this is because we don't have to graph it, we don't really need a graphing calculator to help us. We don't need graph paper. We can check it that way. That's fine. And we can deal with variables that aren't x's and y's, which we'll see later on. And we can also deal with decimals and things like that without worrying too much. So again, the steps: choose one of the variables in one of the equations to solve for. I'll solve for this x, just because I get to choose one. My next best choice might be to solve for this y. So this equation will be x equals, I'll add 0.4y to both sides, so I get 0.4y minus 16. And then I'm going to substitute that part into the x value of the other equation. So you don't technically have to rewrite the system if you just rewrite it like this. So my next step will be 2, but instead of x, 0.4y minus 16 plus 1 more y is equal to 13. Again, a little distributive law, 0.8y minus 32 plus 1y is equal to 13. 0.8 and 1 is 1.8 y's. Add 32 to both sides and get 45. Dividing both sides by 1.8. That might require a calculator. Gives you 25. And then back substitute, and you can use either equation. Seeing the decimal places in one of the equation doesn't really entitle me or want me to substitute into this equation. So I'm going to use the 2x plus y equals 13 equation and say 2x and substitute the 25 in is equal to 13. Subtracting 25 from both sides is negative 12, and dividing by 2, and I now have my solution of x is negative 6 and y is 25. One last example for you. Sometimes equations are already solved for one of the variables, and one really nice example is when both equations are already solved for one of the variables. So y is already solved for 3x minus 1, so I can substitute that directly into the other equation. So then I get 3x minus 1 is equal to 2x minus 7. This is great. If you can, make it y equals mx plus b and think about this as y1 and y2, then you're basically making y1 is equal to y2, and you're solving it. So it's fairly easy to solve. Subtract 2x from both sides, add 1 to both sides, and then you still have to do the back substitution. So choose one of your equations, substitute in your x value, and calculate to get a final answer, where x is negative 6 and y is negative 19. If you have time, you can always double check your solution. It should be a solution to both equations. So I should be able to substitute negative 6 in here and get negative 19 as an output value. And I should also be able to make x is negative 6 here and get negative 19 as an output value. All right, that's all for today.